We just finished the entire 7-layer reference model. Now, let's take a look at some of the statements about them in the courseware. We define a 7-layer reference model here. Everyone can see, after we define the model, an effect we can achieve as a whole. First, during our entire networking process, can reduce the overall complexity of our network. Why do you say so? Like we do a problem or solve a problem. If we divide the steps and solve them by level, relatively speaking, every step we take is simpler. If the future for a complex problem, we just stack all the questions together. So in fact, for the network communication as a whole, the development of our program and the process of future implementation is relatively difficult. So this will involve a complexity problem. No problem. After, it's the standardization that I've been talking about. When all our manufacturers are based on the same standard to production and manufacturing equipment of all the networks made in the future, devices that need to communicate follow a complete set of standards. So in the future, whether it is product development, application development, or the overall troubleshooting process in the future, are relatively more standard. Module is a concept of our layering. Each layer is equivalent to a separate module. There is a collaborative relationship between the layers and when we fully develop each level. In fact, based on each layer, we will develop some corresponding different protocols. In the future we will learn, based on each layer in our specific provisions, or various manufacturers. We are based on Cisco. What privatized agreements does it have? These are the directions that everyone can learn in the future. That is, when we define each layer clearly, we want to achieve, make improvements to a feature at each layer, are relatively simpler. The second is the last mentioned. It is convenient for everyone to carry out a complete teaching. All right. Let's take a final look. Each layer it gives a whole process. Let's get this right. For the OSI reference model, let's first look at the physical layer. For the physical layer, what is passed between our devices is called a bit stream. It is equivalent to what we are passing is the level signal. High and low level. We specify the overall transfer rate and the transmission of our overall signal standards. This is what our physical layer accomplishes. For the data link layer, it also belongs to the physical layer. We finally put the level signal through the network port. Bits converted to 0101 binary. Then our data link layer. It is to put the binary code like 0101. Combine it into bytes. After that, we will combine them into the frames here on our second floor. Data frame. And use the MAC address of the data link layer to access the data as a whole. And an error detection function. This is what we just talked about. We finally make a conclusion. An address provided by the network layer. Logical address. You can see the difference between them. Why is the network layer called a logical address? Because for the network layer, its address is not like a MAC address. The MAC address itself has a small feature of its own. We all have IPv4 addresses on our computers. For my current device, IPv4 address is not assigned by me. But it also doesn't come with my device itself. Instead, it is automatically issued through a dynamic host configuration protocol, such as DHCP. It's called a logical address. It is modifiable. That is, people can modify this parameter. And for MAC addresses, it is also called physical address, also called network card address. This address is shipped from the factory. Each NIC is shipped from the factory. Will burn into a MAC address in the network card chip. We call it a physical address. This address uniquely identifies you. Network card to use. It can't be changed. So we call it physical address. Also put the IPv4 address. IP address is called logical address, because this is what you can configure. Then it is called for the router to determine the path. This is the function we are talking about. Routing via routing. This is our 3-layer network layer. Further up is the transport layer. The transport layer provides connection-oriented or connectionless data transfer. What does this mean? Let's take a look. For our connection-oriented, it's the TCP we just mentioned. Connectionless is actually referred to as UDP. If we are using TCP, in fact, we will mention a concept of retransmission. Later, we will show you the transport layer. I'll show you when I talk about packaging. Then comes the session layer. Everyone can see. Overall, the concept of this communication session. You don't need to care too much. What I told you in class just now is server requests between different applications. Right. Here's what we're talking about. Respond to the concept of such a level. Just as understanding. Including presentation layer, encoding of data. Application layer. Our layer closest to the user. Overall to provide all the unrealizable functions of the lower layer. This is our 7-layer reference model. A series of functions that they implement. As we understand. The next step is to explain data encapsulation. Before talking about data encapsulation, let's take a look first. More basic concepts. Before talking about the reference model, we talked about the overall architecture of the network. So, similarly, we also put a few pictures in the courseware given by Cisco. Explain to everyone. Let's first look at this architecture. This is our network. We won't mention how to burn. This is just a means of industrialized production equipment. This has nothing to do with our communication link. Let's take a look at what is called a network. First of all, in this picture, here's a home office. Have a mobile users through the internet. So there's a headquarters here. Let me tell you, this is the headquarters. When you take the CCIE exam in the future, we'll see this scene. Alright. You will see you later in the exam. It's abbreviated as HQ. So what is this on the left? Branch office. It's a division. Also called a branch. Everyone can understand. For such a picture. In the future, everyone will maintain the network. Our more typically maintains an enterprise class network. Pay attention to what I say. We maintain an enterprise class network. To be honest, the very beginning of our maintenance is a set of enterprise network. But the business we are talking about doesn't have to be a company, such as what we call companies, schools, hospitals, governments, some such organizational units and institutions. It's actually called an enterprise class network. Can you understand? Because it belongs to a set of enterprise-level network models, or what we call the campus network. Actually, it means, what is enterprise network? When talking about the overall network architecture, I mentioned the concept of a local area network. When we use the local area network in the enterprise network environment, we'll call it the enterprise network. It is the network according to the overall use area, divided into a company. Such a local area network within an enterprise. Look down. This is a simple network. 2 terminals. We hold a medium among us that can carry data. For example, a network cable, connected by such a transmission medium. This is a simple network. That's in the future, except for this. Please pay attention. Virtually every device. There must also be what we call a network card, or network port, network interface. This line, the crystal head in the middle, to be plugged into our network port. Then your final electrical signal. It is compiled by our network card or network port, and converted into 0101 binary. And if both parties want to communicate, must follow the TCP/IP protocol stack. So the network cable we are talking about now. How to make a simple network. The network card and the protocol stack are 3 elements. Is indispensable. Please pay attention. NIC and our protocol stack. It must be present at the same time. Otherwise, there is no way to connect our network. Simple network. Let's look at some common physical components. In the lower left corner we see an RJ45 connector. It's a standard. This is a standard for twisted pair. Let's just say, it actually involves a line sequence. 2 production line sequences of 568A and 568B twisted pair. It has a lot of some communication standards. For example, it's blocked, unshielded, what we call UTP, STP. If you are interested, you can take a look. In fact, the future is in the project. When we do it ourselves. That is to say, some have a shielding layer on the outside. You can shield the copper core inside our network cable. Is there an electrical signal when transmitting data? Less interference. This is our standard like RJ45. Here RJ45 later. Just know it's a crystal head. Alright. Later we will meet another. Let's say we're in the lower left corner. Have you seen this thing? Have you heard of 2G? In the early days on a very old notebook, we'll insert cards like this. In fact, it is our SIM card. In the earliest, it's plugged into the laptop. It's like I have a wireless network. It is the SIM card of our mobile phone. At that time, the mobile phone signal was still 2G signal. It does not refer to bandwidth. We mean signal 2G, 3G, 4G. Like we have 5G now. 2G is actually equivalent to lasting a long time. 3G later. But 3G has almost no sense of existence. We are already transitioning to 4G. Because the network as a whole has. Communication development is very fast. Let's look down. Down here there is a network topology type. Let me tell you this simply. Future. When our enterprise network. That is, the network architecture of the enterprise. After you have deployed the entire network. We depend on how the network is connected. The general topology can be divided into these types. The first is called a bus type bus topology. What is a bus? That is, you have a line from start to finish. But it is less used now. We call this a shared network. For now, there are not many bus topologies anymore. We now use more. Star and ring. Use more. Ring. As the name suggests, it is my main core equipment now. Note that it does not say all devices. The middle of the core equipment is connected into a ring. Or we are centered on a certain core device. Then spread the network deployment. We call it a new type of network. Roughly like this. But generally it's not so disciplined. It's not that you network. It has to be built this way. Not just with everyone. Just look at their respective names. Their names. Because in the future, we will often come into contact with. This star network on my right. This is what we are most exposed to. What is also called a broadcast network. This is the one we've dealt with the most. Later we will talk about. When talking about OSPF, some topological types like this will be covered. What is the key word here? The key is the word topology. Everyone should know this. What we see in the future, including some of the equipment we painted. Devices are connected to each other. What is this kind of thing called? It's called network topology. All right. This refers to topology. You need to know this word. Further down. It is the basic structure of an enterprise network. Let's just say. For the left. We can see that it is marked very clearly. It's called small business network. What is small business network? Relatively small in size. What's down there? For example, a normal PC, a wireless device, a server or a PC desktop. Let's just assume it's the server. A switch connected to our company in the future. Switch to router. Router to WAN. The operator. Relatively speaking, you will find that its hierarchy is very simple. Terminal connected. Connected through a switch. Export to a router. Go away. Generally speaking, even our router won't buy an enterprise-grade router. This integration. High-performance router. This is our small business network. Everyone can see. Now these two pictures. What is the main difference? Small on the left. On the right is a medium to large network. The main difference between them is that we target large networks. It will be hierarchical. What level? You can see it written here. Access layer. Convergence layer. Core layer. Including some server clusters in the later stage. If the future is open to the outside world, I want to provide some access services. We'll mention server clusters. But now everyone knows. Just have some servers inside. That is, I will join in the future. Equivalent to my current overall network. The scale is relatively large. What are the characteristics of our large network scale? You will find that it has many lines. We are now for the network on the left. It's a single line. You will find between device and device. We will not do any redundant measures. Can you understand? Let's say my line is broken. Don't go online. In the future, my interface is physically damaged. Stop going online. Right. This is what we say. In fact, it is relatively low reliability. We call it the reliability of the network. That is, the ability of the network to resist risks is very small. In the event of a failure in the network, very easy to disrupt your business. It is not optimized enough. But for small businesses, business interruption may not hurt your vitals. It may come back after a period of rush repairs. You're okay. Will not cause serious economic losses. It is good. We often look down. That but to our right. You can see what its features are. There are many lines. First, the terminal below is the same. For example, some PC wireless devices. Telephone. Including some of the calls we dial. And some of our internal servers, etc. These terminal devices. There are also printers and cameras. That can be accessed. Connected to our access layer device. Connected to the device at the access layer. Then the access layer we are talking about. What equipment will be used here? We'll use our layer 2 switch. Let me just tell you here. These devices are generally at the access layer. What they do. It is to connect our terminals to them. For example, there are hundreds of employees, or hundreds of employees in a company. These employees will have access to the internet on their computers in the future. How does it get on the computer? At least I need these computers. Get it together first. Then make it an access equivalent to I'll take it. All one network cable is plugged into the computer. Plug the other end into the switch. Just hook it up first. Later, my data traffic will go out. Take the lead from my switch and go to the internet. At least the terminal comes in first. This is what the access layer does. Access more terminals. That's its mission. Generally speaking, we will learn some technology in the future. For example, snooping of DHCP. We usually do this at the access layer. We'll learn its configuration in your IP. On the internet, we will have a corresponding aggregation layer. Does anyone know what an aggregation layer is? What is the aggregation layer? The aggregation layer aggregates access devices. I will give you an example. For example, this is our terminal. 1 by 1 PC. Very many PCs. Then this is our terminal. Assuming that as our access layer. This is an access switch 1 by 1. There may be dozens of PCs connected to each switch. But is it necessary for the aggregation layer to exist? It cannot exist. First of all, let me tell you about the aggregation layer. It is mainly to aggregate our access layer into one. Everyone can see. It only provides a layer of transit capability in the middle. If there is no aggregation layer, this layer is almost gone. Is it possible? Also. But if there is no aggregation layer, can we connect directly to the core layer? Can also. But what if you have a lot of employees in your company in the future? We know that enterprise machine switches are generally 48 ports and 24 ports. On each switch, you're going to need some redundancy. Is it a redundancy? You can't run out of interfaces. For a large enterprise, you may be hundreds. You can't put all the access switches. All are connected to this router on the egress dot. Can you understand this? Is that not very optimized? And we're going to make a backup. Relatively speaking, we are not so optimized. So what do we actually aggregate at the aggregation layer? It is more to gather our layer 2 access equipment. Generally, we also do some configuration at the aggregation layer, for example, some gateway configuration of some device gateways, including some OSPF configuration, including some DHCP configuration. We send some addresses. We'll all do it at the aggregation layer. It's just all the stuff in here. We may not all learn in NA in the future. Configuration including VRRP. We usually do it at the aggregation layer. You will learn these in the future. Only. Not something we have to learn at this stage. The aggregation layer is generally a switch here. It's just a layer 3 switch. Okay. Layer 3 switch. Everyone can see. It supports us to run routing protocols such as OSPF. It is a layer 3 switch. Below is a layer 2 switch. It is good for us. First, let me tell you, we are actually teaching more for a small business network. So for this architecture, don't think it's complicated, because it's learning slowly. It is not something you must be required to master at this stage. Let's go up. Further up is the core layer. For the core layer, it has a more important mission. In fact, it is also a mission called high-speed forwarding. Core layer. It's like being a senior leader of your company. Senior leadership in general. Think about it. As the decision-making level of the company. They all belong to senior leaders. Senior leadership. They are not very busy every day. Do some low-level things. For example, counting the attendance of lower-level employees. This is what the access layer does. It's the work of some people at the grassroots level. The middle layer of the company is like the aggregation layer. Manage company affairs. For high level. Focus on making decisions every day. The same is true for the core layer. What do we usually choose for core equipment? To be honest, many companies will buy firewalls at the core layer. Here we draw the router. But everyone will know. In fact, many enterprises use firewalls at the core layer. Why? Because of the firewall. The firewall itself. It has a lot of routing functions. That is, basically for a business. Routing functions that enterprises need to use. Firewall devices are basically supported. Second, it also provides security. That is, if I buy a router separately, then if I want to ensure some security of the intranet, defend against attacks from the WAN, I have to buy the firewall separately. So now, very many firewalls, regardless of the manufacturers, they all naturally come with many routing functions used in the enterprise. So in the core of the export here, in many places, the firewall is actually directly used. Only larger enterprises will use routers. Then it will go to the external firewall again. So this is what we're going to talk about. Some of its architectural issues. All of these need to be understood. Let's say one last thing. That's the problem with the server cluster. That is, there will be some servers in our enterprise. In the future, we will learn some safety. Some trust zones. DMZ. All of these will be learned in the future. But it's safe. Because here it is also drawn. Firewall. So for our current equipment. For us now. Suppose we also have firewalls here. Because of the exit here we have a router. Including routers can now also to some extent implement some of our corresponding security policies. It's all okay. We can also deploy security policies on firewalls. Externally we can also provide relative access service and ensure the security of the server. It's all doable. This is our overall communication architecture. So for large networks, it actually does better. The first point we call redundancy. What is redundancy? You can see each aggregation layer. Do I have two devices? Every device at the access layer. Is it all connected to the gathering? It is equivalent to if a device hangs. Change a color. If the device hangs. In the future, I can still go this way. Our core layer is also two devices. Your device will hang up. My traffic can still go this way and then go out. Can you understand? So it is equivalent to each layer. We will have more options. We call it high availability. High availability. And it is very safe. Because we export can do strategies accordingly. Or by the corresponding firewall. And we are more scalable. These are some of its mechanisms. Or some features are called extensibility. Why is scalable? You look at each layer. Relatively speaking, they have done so many backups. If the future is for the access layer, I want to introduce more terminals. I add another access layer device. Then connect to the original network. Because for the upper, is it all planned? Look. I'm coming in now. Just need to be between our second floor. Let's do a relative redundancy. because the upper layers do not need to be edited. So in the future I will add a switch. More data. In other words, the access of our terminal. It is very easy to extend. That is, the more rules are built for your network, the clearer your hierarchy is, and the more regular the network deployment. You will find that this is a very good structure. Then in the future, you will expand the network as a whole. For example, your company has a new business requirement. You are now going to expand the network. It's all very, very convenient. This is basically some form of their communication. At last, let's look at the duplex mode. Take a look at the duplex mode. For our duplex mode there are two techniques. One called half duplex. A duplex. What's the difference between them? Very simple. First let's talk about half duplex. It's like a walkie-talkie from our early days. Concept of walkie-talkie. What is a walkie-talkie? At the same time I press this button and talk, I'll take up the entire channel. Others can only listen to me when I speak. The same moment. For a communication mode such as a walkie-talkie, you can't talk to two people at the same time. Don't support the two of you talking to the outside world at the same time. Half duplex is just that. For us at the same moment. It does not allow us to perform both data uploads. Data download. That's the one. Our physical transmission link. We are absolutely only at the same time. Single item data transfer in the same direction. Here's what we're talking about. Technologies such as half duplex. And in our half duplex technology, it will have a data conflict problem. Then we have an older technology called CCNA, Carrier Sense Multiple Access Collision Detection Technology, to solve this problem. But now this technology, basically there is no use seen. So you don't need to pay too much attention to it. We're basically hardly seeing half duplex now. Except in some extreme industrial environments. That is, in some networks less than gigabit. For example, some robotic arms. In such an environment, you can still see half duplex. Now in our overall internet data communication, half duplex has retired from the stage of history. Because its efficiency is too low. That's it. Duplex mode. Let's look down. Full duplex. As opposed to half duplex. You can see its arrow. Draws a two-way arrow. Stands for full duplex. It's like we call. What are the characteristics of calling? I can hit you at the same moment I'm talking. When you fight me, you can also talk. For example, a phone call to quarrel with someone. The two of you can argue at the same time. If it is a walkie-talkie, you just have to wait for it to finish first. Then you scold back. Wait until it finishes scolding you. And then scolding back. That is, we have more freedom of speech as a whole. For data communication. That I can upload data. Data can also be downloaded. Non-interference between the two. But please note. Two duplex modes. It supports both upload and download. It's just that. Half duplex doesn't support doing two things at the same time. Full duplex support. Instead of saying, half duplex can only support upload. Or only support download. First of all you need to know this. Row. Then we basically this PPT. Almost finished. This is the part above. We next. We then go down to the data encapsulation process. We actually said a lot just now. Said a lot. But specifically for the transmission of our entire data. We just talked about the 7th floor. Now I'm going to talk about what exactly I'm saying. That is to say, Each of our layers can perform the function of each layer. So how to implement the function of each layer? You see what you say. Layer 2 can complete the check and have a MAC. Layer 3 has an IP. Layer 4 has a port. We will not mention the application layer of the 5th, 6th, and 7th layers for the time being. That specific port of each layer. Where is this IP address, this MAC address? Don't worry. Then we will talk about how to implement the part of our model today. That's where we are. Data in its entirety before sending. We will have a word called encapsulation of data. So what does data encapsulation mean? Like wearing clothes. Data will be found. We as an end user. This is called sender. I want to send a data to the outside world. Then before sending the data, you will see that there is a user date. We usually say, this is called business data. The future company. The whole we run carries real data transfer. We call it user or business data. I generate a data locally. Like I sent a hello on WhatsApp. Then the data I sent is actually what I want to deliver. Now comes the problem. Our device. I'm just producing a hello now. This data. If I don't go through any other. We are talking about the identity of each level. That first. My device knows the data I generate. What does hello mean? It is not known. The second hello. Who are you going to tell? Do not know. Where do you want to send this hello in the future? How to pass? If the other party does not receive. Do you need any response? I don't know all of this. What is this like? You want to send a courier outside. You're packed now. You took a piece of tape and wrapped it around. Put it here. There is none left. You thing. Neither tell anyone what courier company you choose. Don't tell anyone who your device is. Don't tell anyone where you send the courier. Then you can't send this data. Can you understand? You are equivalent to generating a character locally. You can't send this. So you want this hello. Arrive at another person. For example, your friends. Your netizen receives this hello on its computer. You have to have a transfer process. Then during transmission, we need to carry out layer-by-layer data encapsulation. It is equivalent to adding a layer to your data. Add another layer. To ensure that this data can eventually be via the internet to the peer device. Reach the peer device. Reach the peer application. And arrive at the overall page of the peer. And compile and display it in front of it. So the overall process. It requires all our layers to cooperate with each other. Let's not talk about the upper 3 floors. We can see that at each layer it will write L here. L means level. Add a 7-layer header. Application layer header. Add a 6. 5 floors. That is our current presentation and session layer. We won't talk about this. After the top 3 layers are added. How big is our overall data? You'll find it's so big. You will find the original. This data is only so big. After the 3 layers of headgear are finished, it will be so big. Don't care. What does it cover? It's the various functions that I'm talking about. Next we get to the 4th floor. In 4 layers I will add a new header. It is our 4-layer header, which is the header of the transport layer. Here we will identify the port. And will identify the original port and the destination port. The 2 most important parameters are here. After the 4th floor is over, our data has become even fatter. Then go to the 3rd layer. And continue to perform encapsulation. In layer 3 we will encapsulate the source IP, destination IP. What is the IP of my device now? What is the IP of the peer device I want to reach? We'll mark it here. Equivalent to what would I fill in on the third floor? Sender and recipient information. Further down. What will we fill in on the second floor? Source MAC, destination MAC. When data forwarding is performed on such a link, exactly which MAC address am I from? What MAC address did it send to? We want to identify. Second, we now add a tail to the second layer. This FCS is one of our frame check sequences to verify the overall integrity of the data. It is the function performed by our second layer. If the future fails to pass the FCS verification, we'll drop it. Just tell everyone here. For our second floor, what is the concept of this FCS? In the future, if I send the data as a whole, everyone will find. Isn't this data encapsulated layer by layer? When it was sealed to our second floor. Has it been this long? Right. It's been so long overall. Then we will do the verification of the FCS we are talking about. This check is called CRC. Cyclic Redundancy Check. So which part does it verify? It will check this part of the whole algorithm to calculate a value and fill in the FCS field. That is equivalent to that we are now encapsulating the overall head and figured out a value and filled it in this field. What is this data for in the end? Data goes through our transmission medium, passed to the other end, to the peer. Wait a minute, we talk. The peer has a decapsulation process. Everyone first enter this FCS. We checked first. It is good. Then let's look down. How big is this packet after the overall encapsulation? We should mention in this lesson. Wait, when it comes to MTU, I will tell you about this concept. It depends on which protocol are you using for layer 2 now? In the second layer, the more standard we are using now is Ethernet 2 frame. If you use it, our final data size is. We will talk about the last 1518 today. I'll tell you all in a while. We will refer to an MTU value and a package involving the second layer. It's a length. But this actually does not require you to master. We're going to look at data unpacking next. The process of unpacking is actually corresponding to just now. We first, when the data is received from the physical layer, we compile it through the network card into a binary bit stream, code for 0101. We are about to start unpacking to the second layer here. We're going to remove the head and tail of the second floor. So first note here at the end, we have to check the FCS again. That is CRC, Cyclic Redundancy Check. We will calculate again. Use this algorithm to calculate all the previous data. Generate a value. After calculating this value, do a comparison with this FCS I received. If the comparison result is successful, prove that my data is error-free during the intermediate transfer process. Then I will do the up delivery. Perform the next round of decapsulation. Guys, this is an algorithm we call it. That is on the second floor. We can verify data integrity. If the data now finds out what it says to us. Reach the peer. When the peer end encapsulation is unpacked to the second layer, find data errors. Then I will directly lose the packet and will not process it downward. You must know this. This is what we call this. Okay. Let's go on. We have finished the first and last floor of our second floor. We're going to look up for 3 layers. We are still going to continue to decapsulate. We're going to take off the 3-layer header now. Continue to the 4th floor. For the 4th layer, Remove the head of the fourth layer. 5-level solution. 6-level solution. The final 7-layer encapsulation is completed. We can reveal the most original data content. Can you understand what I mean, classmates? So for our current overall data, we are now complete with all 7 layers of encapsulation. We can only see user data when we reach the peer. Then all of our packages, all just for the future in transit, can help data. Just a means to reach the destination smoothly. This is called data encapsulation and decapsulation. This is our point.